Greetings. In our previous video, we had ethane, which initially was at 10 megapascal and 100 degrees C. Of course, it was a certain mass of ethane. The problems don't usually tell us that straightforward, but we have to assume it for the problem. There's no other way to it. Initially, it was at 10 megapascals and 100 degrees C, and in a constant pressure process, its volume expands 60%. I mean, the second volume is 1.6 times initial volume. And we want to know what the final temperature is. In fact, if we want to learn some physical understanding of this problem, assume that there is a cylinder piston device. Assume that ethane is in a cylinder piston device, and initially it is here. P1 equals 10 megapascals, and T1 equals 100 degrees C, and it expands such that V2 equals 1.6 V1. So if we want to do it just as we have always done, and you see the problem doesn't tell us always to assume such a thing, it just tells us that it's initial and final conditions, then we could write the mass conservation law, dm cv by dt equals m dot I minus m dot E, and since nothing enters or leaves our system, we have to assume a system, and the system is the ethane gas inside here. Okay, we have to assume an ethane gas inside here. This is our system, and therefore M2 minus M1 equals 0, or V2 over V2 minus V1 over V1 equals 0. And since V2 equals 1.6 V1, we will conclude that V2 would equal 1.6 V1. And this is the structure where we want to solve specific volumes from the knowledge that we have. Now, we solved this problem for perfect gas, and now we want to solve it for real gas. Well, this is our compressibility chart, and what it basically tells us is this is our equation. This is our real gas equation. And if you want to draw this equation in a chart to visualize it, this is it. This is what it is. Visualization of this equation. Well, to use this chart, what you have to do is to impose our problem on this chart. And to do that, for initial condition, PR1 would equal P1 divided by P critical for ethane. And that would equal, we know that initial pressure is 10 megapascal and P critical is 4.48. And the outcome would be 2.232. This is our reduced pressure that we have it here. This is the this axis. Okay, this is our horizontal axis, and our value would be for PR1 would be somewhere on this line where we can, of course, draw it like this. I mean, this is the line for 2.232, and we know that our um, problem would be somewhere over here. If we calculate TR1 equals our temperature, which is 373.15. Remember that it's 100 degrees centigrade, but we have to change it to Kelvin. So always we have to change it to Kelvin, divided by 305.5, and the outcome would be 1.22. This is TR1, and therefore, with a knowledge of these two, we can find our initial point on this diagram. You see, this is 1.2, this is 1.3, you see, this is 1.2. These lines, these full lines are TRs. One is here, 1.05, 1.1, 1.2, and 1.3. So we are here and on a line 1.22. It would be somewhere around here. And I have just put it down with a green star. This is our point 1 on this chart. And once we know our point, we can do two things. I mean, we are using this equation, but on a chart. So we could read Z from it, which is somehow 0.59. And also on these dashed lines, you could read VR from it. So Z, Z for point 1 is 0.59, which is somewhere here. Okay, this is Z, and VR is somewhere between 0.3 and 0.35. I assume it to be 0.33. So VR equals 0.33. This is VR is non-dimensional, and its definition is here. Its definition is here. You see, its definition is on here. VR equals V over critical point specific volume if our ethane was perfect gas as at critical point. This is how VR is defined. Since this one is constant, so if between points 1 and 2, V is 60% higher, therefore VR would be 60% higher. Okay, now what we do is to calculate VR for point 2. This is VR1, and VR2, VR for point 2 would be 0.33 times VR1 times 1.6, and that is 0.528. You see, we now know that our final point is on 0.528. This is line point 5. This is line point 6. So 5.528 would be somewhere around here. Our process is constant pressure. So at final condition, PR would be the same as initial condition. And if you want to learn about the initial and final condition, this would be our final condition, condition 2, and this would be our initial condition, condition 1, which are denoted in green. This is our final condition. And if we just read these values the from this chart, we would learn that Tr2 equals 1.45 and Z equals 0.8. These are the values that we read from the chart, and which, as I said, this chart is exactly a graphic representation of PV equals ZRT. It's graphic representation of this equation. So, with the knowledge of TR2, that would be very simple to calculate T2. T2 would be 1.45 times the critical point, critical temperature, which is 305.5, and that equals 443 Kelvin. Remember that ideal gas assumption, and I will put it red to show that is not the correct value, just to compare. Ideal gas assumption would give us T2 equal 597.04 Kelvin, which is far different, but it's not strange, it's not surprising, since you see when was initially Z was initially 0.59. Okay, Z initially was 0.59, and finally it was zero point 0.8. So you expect something around 40% error, and 40% error in 443K and 597K. This is about 600 Kelvin, 440. So 200 Kelvin error in this range would be something about 40% error, which our Z is taking care of. But this is the correct value since it has assumed real gas, and this is the wrong value for effect gas law. Is not valid for ethane in this range of temperature and pressure. Thank you very much for watching, and cheers.